Okay, now we're going to talk about phase changes and states of matter and how our structure of our molecules affects these things. First, we have some vocabulary to review. So, I think we know what solid is, liquid and gas. When we go from, solid to a liquid, we are melting. Our energy is increasing. We have to add energy to go from a solid to a liquid. Hold on a second. I'm going to draw a heating curve in a minute. That's another way we looked at this. When we go from a liquid to gas, we are vaporizing a substance. Often we are also boiling it, but going from liquid to gas is vaporizing, and again, we have to add energy to something to go from a liquid to a gas. So these are melting and vaporizing are endothermic. If we have a gas and we condense it back down to a liquid, we are losing energy. The word from going from a gas to a liquid is condensation. And when we go from a liquid to a solid, we freeze. Again, that is also exothermic. We are losing energy. When a liquid goes to a solid, actually energy is released. That's why lots of times when it snows, the air outside will get slightly warmer as it's snowing, which is kind of interesting. If we go straight from a solid to a gas, which is what carbon dioxide does at 1 atmosphere, that's called sublimation. It's endothermic. And if we go from a gas to a solid, we are exothermic. We are losing energy. Another way, when we showed this last year, was with a heating or a cooling curve. We drew something like this. You drew it in my class. This is energy increasing this way. This is temperature. So as you add energy, as you go this way, this is a solid. You're solid here. At some point, you start melting. While you're melting, the temperature does not change because the kinetic energy is no longer increasing. Once you finish melting, the energy that you're adding can cause the kinetic energy to increase until you reach the boiling point. At that point, you'll start vaporizing. The temperature, again, will not change during that process. Once everything you have is a gas, then the extra energy that you're adding can increase the temperature of that gas. Where in reverse, you go from a gas back down to the vaporization point. The vaporization point is the point at which you vaporize or which you condense. It depends on your direction. Once you've condensed everything to a liquid, if you continue to cool down, once you reach the freezing point and the melting point are the same temperature. When everything's frozen, only then will the temperature of your solid start to decrease. So a little more vocabulary. Melting is also called fusion. The heat of fusion, the heat of melting, is the energy required to change a solid at its melting point to a liquid. Vaporizing is going from a liquid to a gas. It's the energy required to change a liquid at its boiling point to a gas. We use the heat of fusion when we want to calculate how much energy we need to go from a solid to a liquid. We also use the heat of fusion, the opposite of the heat of fusion, when we want to go from a liquid to a gas. A liquid to a solid, to go backwards. We just change the sign. In this graph up here, we have some heat of fusions of different substances: butane, diethyl ether, water, and mercury. And we can talk about why the heat of fusion is more for diethyl ether than it is for butane. Remember, fusion is going from a solid to a liquid. It's actually less for water than for diethyl ether, and it's much higher for mercury to go from a solid to a liquid. Then if you look at the heat of vaporization, that increases as you go from butane, comparing these things. Think about why the heat of vaporization for each substance is greater than the heat of fusion for each substance. And we can talk about that tomorrow. Here is another heating curve, like the one I just drew, except with labels. The heat added to a system at the melting points, or the fusion points, and the vaporization points goes into pulling the molecules farther apart from each other, so the temperature does not change. I think we'll work these problems in class tomorrow. I'm going to jump forward to vapor pressure. So vapor pressure is defined as the pressure exerted by a vapor when it's in equilibrium with its liquid or solid phase. So if you think about what equilibrium means no change. So when something, let's look at this picture. I'm going to do this. And so here we have liquid ethanol. So I'm going to go like this. So all the molecules in the liquid are moving, and at some point the ones that are near the surface, if they get enough energy, they can make a break for it and they can become vapor. Okay, they have to have enough energy to separate themselves from the intermolecular attractions to the other liquid molecules. So they have to have enough kinetic energy, be moving fast enough that they can, when they're near the surface, separate themselves from the forces that are attracting them to the other molecules. So some molecules are always doing that. We call that the pressure exerted by the molecules that successfully break away from their friends. We call that the vapor pressure at any specific temperature. At any temperature, for any liquid, you're going to have a certain pressure. These, we haven't talked about gases yet, because I'm going to have you do that over the break, but as molecules move around, pressure is force over area, so molecules in a gas exert pressure by hitting the sides of a container. So the ones that make escape, their liquid friends down here and are moving around here, they're going to hit the container sides with a certain force and create some pressure. And we call that the vapor pressure of a substance at it. Now, at some point, sorry, I was getting ahead of myself. So in a closed system, there will be an equilibrium. The molecules that are escaping will escape at the same rate that some are being recaptured. Some of these little molecules get too close to the surface of the liquid and are attracted by intermolecular forces. So in a closed system, you're going to have what's called equilibrium vapor pressure, and the amount that are breaking free are going to be equal to the amount that are getting caught, and so you're always going to have a fixed number floating around in there and creating a pressure. This is in a closed system, because in an open system, what would happen is some would break free, they'd be moving around, but then they could leave the system. Woo, they'd get out, and then more would break free, and that's how evaporation happens. Even though some would get recaptured, if it's an open system, they can leave the container. But in a closed system, you have what's called equilibrium vapor pressure. And since temperature is a measure of kinetic energy, at any temperature, some molecules in a liquid have enough energy to escape, but as you increase the temperature, you increase the energy, and so as the temperature rises, the fraction of molecules that have enough energy to escape increases. Another vocabulary word, the word volatile, that means evaporates easily. And liquids that have a high vapor pressure evaporate easily. A high vapor pressure means a lot of them are leaving their liquid friend, their friends that are trapped in the liquid. You have a lot of them that are leaving. That's a high and bouncing against the walls of the container. That's a high vapor pressure. Liquids that have a high vapor pressure, if they're in an open system, will evaporate easily. We call that volatile. Nail polish remover, gasoline, those are volatile liquids. So what I want to think about here is the relationship between volatility and intermolecular forces. What is the relationship between volatility and intermolecular forces? Well, if you have strong intermolecular forces, and these molecules are really attracted to each other, it's going to be harder, if they're really attracted to all their friends in the liquid, it's going to be harder for them to break free. However, if I have another container and I have very weak intermolecular forces, then it's going to be easier for these guys who are very weakly attracted to each other to break free. So weak intermolecular forces, weak, W-E-A-K, weak IMFs equals more volatile substances, more volatility. So you can think about these other two questions. We're going to answer them in class. Now we're going to define boiling point. So boiling point is technically defined at the temperature at which a liquid's vapor pressure equals atmospheric pressure. So then, and then another definition that the word normal doesn't mean what you think it means. The word normal means the boiling point when the vapor pressure is is the temperature when the vapor pressure is 760 torr, because this is standard pressure. Standard pressure is defined as 1 atmosphere, which is the same as 760 torr. You're gonna study gases and review all this stuff. And a word we call the normal boiling point is the temperature at 1 atmosphere, the temperature when the vapor pressure is equal to 1 atmosphere, or 760 torr. So let's think about why we call this the boiling point, we define the boiling point as the temperature when vapor pressure equals atmospheric pressure. So we have a liquid, and as every so often some molecules are breaking free of the first surface, but, and again, we haven't studied gases yet this year, but we did last year, there is a weight on this liquid, and that is the weight of air. Weight is the wrong word, I should say. There is pressure being exerted on this water by the air around it, or whatever happens to be surrounding it. I'm assuming this is a beaker of water and it's surrounded by air. So all the air molecules are moving around and they have a certain amount of energy. And then as they hit the surface of the water and everything else, they are causing pressure. So wherever you are, whatever's surrounding you has pressure. In this case, this air surrounding this beaker has a pressure, and let's say that it's just standard pressure, so it's 1 atmosphere or 760 torr, same thing. So what happens is as we heat up our beaker of water, let's assume we're going to heat it up, our molecules get more energy, so they start to move faster and faster, and as they move faster and faster, more of them get energy to escape. So more and more of them are escaping, but they're still being prevented from escaping to a certain extent by the pressure of the air that's surrounding them. Until you reach a point where the pressure of the molecules when they're escaping is equal to the pressure of the air, and that's boiling, because then the pressure for escape essentially is equal to the pressure of the air that's holding them in. And that's when you start to see, oops, wrong color, well, I'll do it in black, bubbles form in your water, because then there's really nothing preventing everything from escaping. The ability of our molecules to escape has equaled the ability of the air pressure to keep them down. Hopefully that helped. But, so that we define boiling point as the temperature at which the vapor pressure equals the atmospheric pressure. Okay, let's consider these questions, which relate to the graph in the previous slide. Estimate the boiling point of diethyl ether under an external pressure of 0.8 atmospheres. And which of the four substances has the largest intermolecular forces? Explain. So first we're going to estimate the boiling point of diethyl ether at 0.8 atmospheres. Look at the graph again. Here it is. I want to do this one, not that one. Okay, fine. So here is our line for diethyl ether. And at 0.8 atmospheres, oh, they're going to make us do math, and I don't have my calculator. Darn it. So we'll do this one in class. But 0.8, well, we'll just estimate right now. 0.8 atmospheres is about 8/10. So this is 1 atmosphere, 760 torr. So about 8/10 of that would be somewhere around here. So if we go over here and we find the vapor pressure at that pressure, that's here, we can scroll down. The boiling point would be about 25 degrees Celsius. So we can go over that in class tomorrow with an actual calculator. Now let's see which one of these has the strongest intermolecular forces. So let's think about that. Which one do you think has the strongest intermolecular forces? Intermolecular force. Well, let's just pick a temperature just to compare. We'll go to 40 degrees. At 40 degrees Celsius, our vapor pressure of water is here. I don't know, that might be about 50 torrs. Our vapor pressure of ethyl alcohol is up here, and our vapor pressure of diethyl ether is right up here. So we have very high vapor pressure comparatively for diethyl ether, and a much lower vapor pressure for water. So what that says to me is that the intermolecular forces holding water together are much stronger than the intermolecular forces of diethyl ether. So water, because its vapor pressure is lower, has much stronger intermolecular forces than the diethyl ether. The diethyl ether, which has weak intermolecular forces, is going to be, and therefore has a higher vapor pressure, is going to have a much higher volatility. So high vapor pressure, high VP, equals high volatility, but it also equals lower intermolecular forces. And conversely, if you have a low vapor pressure, low VP, that means you have higher intermolecular forces because your attractions between your molecules are much stronger, which is why your vapor pressure is low. It's harder for those molecules to break free. So water would have the highest intermolecular forces. Well, I suppose, and if you went out here, the highest intermolecular forces would be between ethylene and glycol. What I'd like to do in class tomorrow is look at the different structures of these substances so we can compare their structures with their intermolecular forces and then the effect that has on their vapor pressure and their boiling points. So I think this video is pretty long now, so I'm going to stop here and we're going to talk about phase diagrams in class tomorrow.